So today I'm going to discuss Modbus communication basics. So while there are a number of different ways to use Modbus, a number of different flavors, I'm going to focus on just kind of standard Modbus and also towards serial, because serial communications is what we have primarily in the oil field in historical devices, but we will touch a little bit on USB and Ethernet as well. All right, so what we're going to go over today is the Open Systems Interconnection, or OSI model, the physical communication interfaces, some communication settings, some analogies or examples of how you can use Modbus, and the details of the communication protocol itself. So the OSI model is a multi-layer model starting from the physical layer, moving all the way up through the networking layers. So the physical layer is the transmission of the raw bits. And then on top of that, we have transmission of data frames. And this is the standard for any kind of protocol. Once you've got those frames, you can take them and network them so that it's routing on a multi-node network, then transporting them or moving them around. The session layer, so keeping open sessions using multiple packets to achieve some presentation layer, and then an application layer. So this is a standard model that's used with pretty much every protocol. And so we're going to go through at least the first few layers for Modbus, because once you really get out of layer 3, Modbus doesn't really matter anymore. It does kind of bleed up into layer 4 a little bit. All right, so the physical layer. So really what it comes down to is two devices communicate using transceivers. So if I want to send data from one device to another, maybe have a response backwards, you need to physically communicate. So if you think about this like placing a phone call, right? So we're going to use telephone lines to communicate between two people, but we haven't really determined what the language is or how fast we're communicating. We're just establishing that first layer of connection. So the transceiver chip is actually an integrated circuit that's sitting on a circuit board and handles the electrical level of communication. So electrical signals going back and forth. So some common ways that you would see communication at this level is RS-232. So this is a standard type connector, a DB9 connector you would see. It's got 9 pins. You know, you're not seeing a lot of this in new devices because there is more efficient, faster communication methods, but still in the oil field, you're going to find a lot of RS-232 devices. The standard right now, especially in hazardous locations, is going to be RS-485. You can get RS-485 into the most hazardous of locations. It can go a lot longer distances because what it is a 2-wire differential. So a lot of signals can degrade over distance, but if you use a differential signal, so you have like a positive and a negative signal, or in this case, we show it as an A and a B, you can go much longer distances. Another benefit of RS-485 is you can do multi-drops. You can actually have up to 32 devices on the same communication line. So it has a lot of benefits from an electrical perspective. USB, I'm sure everybody's familiar with that. It's another serial protocol or physical layer. It gives you higher speed communication, and you can also deliver power. So that's great for a lot of consumer devices where you want to turn a device on and then communicate with it all in one cable. But it is challenging to get USB into hazardous locations. So you might find this like in a Div 2 area, but you certainly won't find it in a Div 1 area. And then, of course, we're all familiar with Ethernet. The best thing about Ethernet, it's really the standard for IP-based communication. So if you want to address multiple different devices, you want to have routing, it is the most flexible and highest speed. And you can also have power delivery, but once again, don't expect to get this into a Div 1 location.
Is now joining.
All right, so if we move on, the actual serial communications layer, once you've actually established a physical communication, you have a number of different settings. And so a lot of people see 9600 8N1, but don't understand what it really means. So I'm going to break that down for you. So the first part, 9600, this is the baud rate. So this is how fast the data is transmitted, and it's in bits per second. So how many different transitions can we have in a second? So you'd see 2400, 9600, 192, right, all the way up to 115.2. There's lots of different data rates or baud rates, and the trade-off is the faster you go, typically the shorter the distance you can run, and the more chance there are for errors. So you'll see a lot of times in historical devices, it's typically 9600 is the default, but as you get better quality connections and shorter distances, you can ramp up those speeds quite dramatically. The next one, the next thing to know is there's a start bit. So at the start of every serial transmission, you're going to get a falling edge. So this says, okay, now I'm going to start sending a data frame in serial, followed by a number of data bits. So in our example here, 9608, that's 8 data bits. And you can change this, but typically the standard is 8 to give you a full byte of data. So those are all done in succession, and those are either falling for a low bit or rising for a high bit, followed by a parity. So that N, meaning no parity, that's once again, in a lot of cases, you're going to see no parity. This is an error detection method. And what it does is it counts the number of odd or even bits, or you can set it to a 1 or set it to a 0. It's just an error detection so that in that bit, you expect it to be a certain number. So you can count up the bits and see how many odd bits there are or even bits. It's a very basic error detection. And then a stop bit. So then we have a rise. It can be 1 or 1.5 or 2, but you're typically going to see 1 stop bit. So 9600 8N1 is 9600 bits per second, 8 data bits, no parity, 1 stop bit. So now this becomes the fundamental thing that we can build serial Modbus on top of, because now we can send a byte of data at a time. So the next layer is the data link layer. So we want to link 2 different devices using Modbus. And so in Modbus, we have a Modbus master and a Modbus slave. So there's one device or computer on the network that is the master, and it controls all of the different slave nodes. So it is a pull response protocol, which means that the Modbus master first has to ask the slave for something, and then it responds. The slave can never speak until spoken to. And it's done in a round robin fashion. So this is one of the, in serial Modbus at least, is an inefficiency of Modbus, is this Modbus master can't move on to the second slave until the first one responds. So if you ever have a node on a Modbus network that doesn't respond or takes too long to respond, it will slow down the communication with all of the devices. So in a lot of times you might, want to have a 10-minute round robin between stations. That can vary depending on the number of nodes and also how long they take to respond or if they're offline. So the Modbus protocol itself, it has 2 different ways to transmit data. So ASCII, so this is using characters. So instead of sending, 18,095 as a number, it has to be sent as 18095. So that actually takes 5 bytes of data or 5 characters. If we use RTU, this is actually sending binary data. So what we can do is we can represent a number up to 65,536 by using 2 bytes. And so we're using only 16 bits of data here. So you can see it's quite a bit more efficient. Now, ASCII was used historically for poor quality serial communication because you have more data you're sending and you know what valid characters can be sent. So you have kind of inherent error checking. But what I see today is most communications use RTU. You have a max message size of 256 bytes. And then you've got valid addresses. We're using a very small set of addresses. The Modbus protocol actually reserves the last 7 addresses or 8 addresses, 248 to 255. So you have to make sure that you never use those numbers. And then 0 is a special code, which we reserve for broadcast messaging. So if you want your master to send out, an update to all 200 slaves that you might have connected, you can just use a broadcast message and they'll all interpret that message and nobody responds to it. So this is what the actual Modbus message looks like. So this is a frame in the data link layer for Modbus. There's always a start pause. So 3.5 characters worth of silence. So this is really important to know is if you're using some radios and your Modbus messages aren't going through properly, sometimes if the radio breaks up the messages, because some messages are going to come through a radio and it's not going to know that it's Modbus. If it puts a break somewhere, it's going to think, the end device is going to think that it's the end of the message or the beginning of a message. So you have to be very, very careful in choosing radios when using Modbus. The destination station is the next piece of information. So it's a single byte that identifies what station it's destined for. Then there's a function code, and we'll get into this in a minute, but this code is going to tell you, what type of data or what type of operation you want this message to act on. And then you're going to send a length plus the data following it. So this kind of package is going to vary in size. So if you're writing a few bytes, you're going to get a length and a bunch of data. And this package or this is going to change with the function codes. You have to look at each function code, because if you're reading something, you're just indicating what addresses you're going to read. But if you're writing something, you need an address that says where, and then the data to go with it as well. So it will vary. And then there's a CRC. So this is a redundancy that takes all of the data, puts it through a mathematical equation, and then writes out this CRC at the end, so that on the receiving end, what you can do is you can rerun that calculation and make sure there's no errors in the frame. And then there's really no way to reconstruct a frame, but you can at least know to throw it away and not act on it. So in a lot of protocols, like when you're doing Modbus frames, there has to be a retry mechanism from the master, so that if the slave throws away the data, that you have an opportunity to retry that operation. And then, of course, the silence frame at the end. Now, this is all for RTU. So this, once again, this is the more efficient way of doing it. But if you're doing ASCII, it's slightly different. So instead of relying on a silence, because you can have any combination of data there, we know that we can use the colon character, so that the actual physical 2 dots are colon. It's character code is used to start the frame, followed by 2-byte station address, as well as a 2-byte function. So once again, we need more data now to represent these things, so they take up twice as much data. And then we can see again here, the length and the data is packaged up in this package. And then there's a longitudinal redundancy check or checksum that's run on this data. So the error handling is slightly different. And this is actually a mistake. It's carriage return line feed.
Unknown
It's not 3.5
participant is now
spaces.
joining.
So there is a character or 2 characters at the end. So very similar. So you have to know if you're ever going to decode Modbus data when you're watching it go by, you got to make sure you know if you're doing RTU or ASCII protocol. And then quickly, we'll just touch on Ethernet. So Ethernet's slightly different because TCP/IP includes a lot of the addressing and stuff for packets. So these are TCP packets. There's a synchronization set of bytes here called the transaction identifier, so that you can synchronize the ordering of the messages. A protocol identifier, length, the station address, the function code, and the data. So there's less error handling built into this, because TCP has a lot of the error handling and routing built right into it. But you can see it's the same kind of payload of data, this function code and this data bytes. So once you actually have frames of network or frames of Modbus data, now we can actually get up into the network layer. So how are we going to move these around, and what are we going to store in it? So data in Modbus is stored in a few different ways, in coils and discretes. So like a single bit is what a coil is, or a discrete. And then registers in standard Modbus are 16 bits. Now, in other flavors like Enron Modbus, this can be 32 bits. For the purpose of this talk, we're going to focus on 16-bit registers, though. And then registers are grouped by this data type. So we group all coils together or registers together. They're not mixed and matched. It's so that we can have common functions that retrieve blocks of data so it can be more efficient. And then each device type. So when you look at a manufacturer or a type of device by a manufacturer, you have to look at what its specific Modbus register map is. So there's not some standardized definition for, plunger lift controllers, for example. You have to look at that manufacturer's definition for their device. So while Modbus is a standard protocol, the contents of the Modbus is not standard. And so you're not going to find consistency between manufacturers. If you buy plunger lift controllers from two different manufacturers, they're not going to work together to have a constant or a common base of registers that you can rely on being the same. So each time you add a new manufacturer's device, you've got to program your system to talk to that manufacturer's set of registers. All right, so this is in general how it's broken up. So when you see a 0 at the beginning and a set of registers, this is coils. So these are read-write binary values. So for example, a valve status, you can read a valve status, but you can also write and output the valve status to change it. Input discretes, so these are single bits as well, just like coils. They're identified by a 1 here. So maybe something like a line pressure switch. Is it tripped or reset? So these are things that we're just going to read. Input registers, same thing. This is an input value, but this is a 16-bit register. So it's denoted by a 3 here. These are, if you wanted to have an analog line pressure sensor value, you'd put it in an input register. And then holding registers, or in some standards, it's just called registers. These are read-write values. So this is something I want to see the status of. So in our controller, maybe the close time for the plunger controller, you want to read that, but you might also want to change it. So it's denoted with a 4. All right, so Modbus Commands. So this is what goes in that function register. I should have probably called it functions here. There's a whole laundry list of different functions, but we'll just go over kind of the main ones. So if you want to read a coil, it's 1, reading input discretes. So this, you can see it's plural here. So if we want to read a bunch of input discretes, if we want to read multiple holding registers or multiple registers, if you want to read multiple input registers, so those are all our read functions. And then you can write single ones. So writing a coil, writing a single registers, writing multiple coils or writing multiple registers. And of course, you can't write the input discretes or the input registers because these are inputs only. So these are the most common functions you're going to find depending on the type of operation you want. And so the function code, you can see it determines both the operation, read or write, and also the range of registers we're going to deal with. So here's an example of a register map provided by a manufacturer. So this is our Modbus guide for our Alien controller. And so our coils, you can see we've denoted with a 0 and 1. This is open. So we want to start the open cycle, or 2, we want to start the close cycle. So we can actually write a 1 to this, and we can change those functions. If I wanted to do something different when writing a 0, we could specify that, but you can see I've only specified one operation here. So those undefined operations, you'll want to stay away from those because it's likely to get ignored, but you never know with certain products what they'll do if you write something that's undefined. And so there are 50 different coils available in our Alien 2 controller. Now, one thing to be careful of per device. So we implement things specifically or exactly as per the standard. So register 1 is actually address 0. And sometimes this confuses people because they'll write something to address 1 and expect it to open. But by the Modbus standard, the register number 1 has address 0, and register number 2 has address 1, and register number 3 has address 2. So there can be an offset there, and some people will specify the address, not the register. So just be careful of that. And I won't go through all of our different registers, of course. It would be a waste of your time, but just a snapshot of some of our holding registers. So remember, 4 is a holding register. So some of these things are things that we might want to set, like a well depth, but we also might want to read that well depth. So that's what we would do with the holding register. So how are we actually going to start to use this, and how are we going to communicate with the device? So we'll take an example of our Alien 2 controller. So this is an RS-485 device. So it's got two wires with a differential signal and a ground. We've got a device here. This is an RS-485 to USB device, and you can use any RS-485 device. We've just packaged up a lot of the different interfaces for our different products into Link. And then we're going to connect it to a PC running Vision. Now, this could be any Modbus master, but what we've done is we've taken our free Vision software and we've added in a Modbus master just to make it convenient for our customers to play with our products. So if you do have our Alien 2 controller and you want to use Modbus or test it before hooking it up to your SCADA system, you can simply do this with an RS-485 to USB device and Vision. So when we go into the Setup tab, you'll notice that there's a couple things to pay attention to. Here, the protocol is serial. So we're actually using a serial connection, and we're using this USB device. And we can actually click this baud button, and it gives me the settings. So the baud rate, the data, the parity, and the stop bits. So you can actually change this for different controllers if you want, or you can change the baud rate if you want to go faster. But the important thing in all Modbus communication is make sure that these serial settings on this side are the same as on the controller. And so you want to make sure you go in and change the Modbus settings to make sure that they're equivalent here. So once we've done that and we go connect, we've now established a connection. Now, no data has been sent because there isn't by the Modbus standard or by serial communication. There's no data being exchanged here at this point in time. So we actually go over to our SCADA tab, and we click on Alien, and it shows us all of the different values that are available for this Alien 2 controller. Now, this has been pre-programmed here, right? So we've set up a screen with all these different values, and each of these values are associated with a Modbus register. So when I click read on this current state, it's going to send a Modbus command to the controller that references the registers that are being used here. They're going to come back as a response. The data is going to be taken out of there and put into the screen. So in behind the scenes, Modbus messages are going back and forth. And actually in our tool, you can turn on a window so that you can see the Modbus going back and forth if you're curious to see what that looks like. So it's a really good learning tool if you've got our product available. And if you don't use our controllers, there's a free simulator that we have that's built in. And what we've done is you can actually run our simulator and Vision on the same computer, and you can talk to them with TCP. So the only thing you need to do is in our simulator, you go into Tools and go Modbus Server, and then that pops up a little TCP settings, and we just use TCP port 6300, and you can start that, and now it's available to receive TCP connections. So when you go into here, instead of using serial, you're going to use TCP, and it's going to connect to the local host. So 127.0.0.1 that's the local host. If you had the simulator running on a different machine, you would put its IP address in there. So you can see we're using the local host port 6300, and this is on port 6300, and we go connect. So we establish the connection between this virtual device and Vision. And then you can do the same thing. You can go in here and you can talk back and forth. So if you want to play with Modbus after this presentation, feel free to download Vision for free. And inside there in the resources tab, you can also install the simulator. All right, so how is this same deployment going to happen on a network out in the field? So the same kind of thing is going to happen. We're going to have the physical controller, and we want to establish communication with a driver that's sitting on a computer somewhere. So what does that driver do? Well, it has all of the register definitions. It's got a pull rate built into it, and its responsibility is to retrieve the data from that remote device. So once again, we're going to establish a serial connection or a TCP connection. We're going to give both sides a station address. In a lot of cases, the master is station 1. So we're going to start at station 2. And once we have these up and communicating, we take that data, and the driver is going to stuff it into some kind of database or historian. So whether this is a Signet system or whether it's a web-based system sitting on Azure or AWS, no matter kind of what the configuration is, there's going to be a driver and then somewhere to store it. And typically this connection is OPC. We're not going to get into that right now, but that driver is going to stuff data at a certain frequency into this database. And then that allows us to build screens that pull from the database. So this is the kind of generic way that data will flow from the screens that an operator is looking at all the way down to a device. All these connections are established. And once this is done once, so this is where all the cost comes in, is building screens, setting up the historian, setting up the drivers, establishing communication between the device and its specific registers. But then you can just roll them out again and again, because that same Modbus register map exists on all of these different devices. So unless you're changing device types, once the setup has been done, you can replicate that across many, many different nodes. So I know that was a really, really quick intro to Modbus. I didn't want to dwell on any one part too much.